Okay, our anode disc. So, the anode discs can be made of different materials. Because molybdenum is a little lighter than tungsten, its atomic number is less than tungsten, we use it as the bulk material. It's really good at handling heat, so it's used as the bulk of the anode. Sometimes other materials like graphite are added on. The shaft of the anode shank, is made of molybdenum as well. Molybdenum's not as tough as tungsten, but it's strong. So toughness is like it's not as hard as tungsten. Okay, you would be able to bend molybdenum more easily than you would tungsten, but it's lighter. It hangs on to heat like tungsten does, and it doesn't warp as much as lesser materials. But it's light. That's the purpose of using it. Okay. So series of ball bearings supported around the anode shank allow the anode to spin roughly freely. There's some friction. That friction creates noise. That's why you can hear the anode disc spinning. You know, even when I spin it in my hand, that's all that noise you're hearing is friction from the bearings in the anode shank touching each other and rubbing against the walls, the inside walls of the copper cylinder in here. So that's all waste. Right? It took me some energy to spin this, right? Some of that energy got converted into sound from these bearings moving, and that is all wasted, okay? The better equipment will produce less waste heat. Newer equipment too, or less waste noise and heat, and so that's obvious. That is an evidence of an old anode. Now the face of the anode, and more specifically, not even the face, because they want to. Engineers are really good at minimizing the amount of work they have to do to get the job done, to get to this, right? They want to minimize the amount of material this takes, the cost, and the complicatedness of the device, right? That's what engineers are very good at doing, because you can overbuild something all you want, but it's going to be overbuilt, cost more money, and it might weigh too much, right? So you want to minimize the amount of material and get the maximum effect, right? So what you'll do is, what the engineers have smartly done is, most of this anode is made of molybdenum, nice and light-ish. The focal track, the place where the electron beam is going to hit, is made of an alloy of tungsten. Alloy just means you have more than one metal mixed together. Okay, so tungsten and rhenium, for example, two metals, right? Different properties from each. When you combine them, you sort of get the best of both worlds, right? So it's embedded onto the anode disc near the outer perimeter. Rhenium gives mechanical stability, where tungsten gives the toughness, the heat retention part of it. Tungsten 74 is our atomic number. Rhenium 75 is our atomic number. So they actually sit right adjacent to each other on the periodic table. For good reason, and I won't talk too much about it till we go to X-ray production, which we'll probably do next class, is the high atomic number means you have very dense material. With dense material, you will have more electrons colliding with the material. Okay, you've probably heard something like to the effect of atoms are mostly empty space, right? So if you have more atoms or larger atoms that are more densely packed, there's less empty space to not run into something. You want to pack them closer together with bigger electron clouds. It's more likely now for the electrons we are sending across to have some interaction on the anode side. Okay, if we made the whole anode side out of, carbon, for example, carbon's a nice material. It's very strong, but carbon's only 6. Its atomic number is only 6. It's very, very light. Okay, and it's less likely that the electrons we're sending across that gap would have an interaction with the carbon atoms. Okay, it's not that the electrons are like a little ball that I throw at a wall, right? So the anode disk is a wall, but it's not like a wall at the macroscopic level. Each little electron interacts with an individual atom, and between the interaction of the atom and electrons, that's where X-rays get made, right? That's chapter 10. So if you want more chance for an interaction with an a projectile electron interacting with an atom of the anode, you want to have a denser, more densely packed anode face, and higher atomic number materials give you that density. Anyways, that's a long-winded way of saying you want dense material for your anode disk. Okay, so you might ask, maybe you don't want to, maybe you didn't think to ask, maybe it didn't come across, but you might want to ask, why does the disk need to spin? Okay, can't I just have maybe a square area, you know, a little block or something like that, where I can just bombard that face with electrons and let it produce X-rays? And you absolutely can. Okay, the first X-ray tubes to be created were stationary X-ray tubes. They had no spinning disks. They were just a little face, little tungsten face that we bombarded with electrons and produced X-rays. Okay, but the area that you bombard with X-rays, or with electrons to produce X-rays, was small, and it would heat up quick, and it would you couldn't make many exposures on it, right? And so if you want to have a greater area, you need the disk to spin. Now, as the exposure is being made, you constantly have a new area kind of coming into the frame of the electron beam and being hit by the projectile electrons. Now you have a track, a circular track that's being struck by electrons, and the disk just spins. It just creates a larger surface area, spreading the heat out over a larger area, keeps it from being concentrated into a small area. Distributing the impacts over a much greater surface area increases the heat capacity for the anode magnitudes. In this case, they say 1,000 times more heat capacity.
So,
yeah.
So the X-rays are only created at the point of the focal point.
Yes.
So once the disk moves on past that point, then you only have heat.
Correct. Yeah. So
the waste product.
It happens so fast that it's almost like, picture it stationary, right? The disk is at this position, electrons hit it, X-rays are emitted, and then the disk rotates a little bit more. More electrons hit it, more X-rays are created, and so on through the whole process, right?
But it's continuous. Continuous at that one point.
Yes, all focused on that one spot in space, and the disk just moves into that spot, right? Moves a new part of the disk continually into that spot as it spins. So yeah, dental X-ray units are often quiet because they have no spinning disk. Okay, there's no bearings, no anode, no noise, less noise at least because of that. Because dental units use low kilovoltage, and they don't need a lot of milliamperage. You don't need a lot of X-rays, and you don't need to have very energetic X-rays to make dental X-rays. Yeah.
To become like a dental assistant who does X-rays, do they have to go through this program, or they can just like?
They take X-ray classes in in their dental program, but it's different. There's no state credentialing, anything like that for dental X-rays. Because the units are fixed, they can't change the exposures on them. All they do is position, they leave the room and make an exposure. There's no risk, there's lower risk for them, but they're still making X-rays. They don't have to have the same credentialing that you do. They do, huh?
And the machine is
A lot smaller, much lower energy. It basically plugs into a wall, you know, it's really, really low energy stuff. And so yeah, they do learn X-ray, and they do get an X-ray certificate from the school that they go to, but they take no state credentialing, and their X-ray certificates are good for life. It's just, you did some schooling, here's your X-ray certificate, you're good to go be a dental assistant, take X-rays. Which is interesting, right?
Do an extra thing to get the skull stuff.
All this extra stuff for all these different no. So yeah, even though they're taking X-rays in the area of the skull, they're not skull X-rays, they're dental X-rays. Different thing. It takes way less exposure to expose teeth than it does to expose the skull. And there's just a lot less critical thinking that needs to be done for dental X-rays. It's not that they don't have a job that they have to do. There's just a lot less critical thinking. There's so much more, which is why you guys go through learning all of this stuff, all the internals, right, how everything works, how you change settings, because you actually have to operate the equipment, where they do operate equipment, but theirs is quite literally pressing the button, right? And there's much less positioning, and it's all right here. You know, everything that they do is right here, and you know they don't have to set a distance, right? The X-ray tube goes right up against the face. It's got that little cylinder on it that keeps it the right distance. There's so much less variables, right? So but yeah, so it's just a different thing. Same stuff that they're using. It's regulated differently.
The
Yeah.
thing they make you chew on, that's the the thing they try to hold in place right when they're taking the
Bite
X-rays.
wing,
That's the image receptor?
Yeah, that's the IR. That's their cassette.
That
Yep.
makes sense.
It used to be a little piece of film, right? Now it's usually attached to a wire now. Comes out of your mouth. So that's the image receptor. Yeah, that is your IR. Yep, teeny little thing. We've got. If you're ever interested and you're here on day when the dental assistants are here, you're welcome to go in and watch what they're doing because it is the same thing. They're doing all the same stuff. They've got an image receptor. It's tiny. They got an X-ray tube. It's also tiny. They've got lead shielding. All the same stuff. It's just everything's done for the teeth, not the rest of the body. Yeah, it's fun to learn about, fun to do, but it is different. Yeah. So yeah, the moral of that though was dental units don't have spinning anodes. Their anodes are stationary. It's just a little spot, little square that gets struck by the electrons. Doesn't move. Okay. I would just kind of skip past this, but the anode discs that we use spin fast, about 3,400 revolutions per minute. Give you rough estimate, that is faster than your car's engine spins when you're driving on the freeway. Okay, your car's engine's usually about 2,500 RPM when you're on the freeway, and you rev them up to go faster, right? But your anode discs spin at several 3,000 or more RPM when they are operating. They only have one speed that they operate at. There are high-speed anodes spinning up to 10,000 RPM. What do you think the high speed does better than the low speed? Like why? Why would we have high speed?
What was the question?
Well, so there's got to be a reason for having high-speed rotors. Why do you think? So if the anode disc spinning helps dissipate heat, what do you think spinning it faster might do?
The longevity of the rotor?
It's not rotor life, because think about it like this: if I spin the anode for 1 minute, right?
Sorry, I meant anode. So the faster that it spins, the more surface that there is to cover.
Okay.
So it's easier for the heat that is coming on to the anode
Good.
to be able to be pushed around in a bigger area.
Good.
So the less heat that's going to be applied to that one area with a lower RPM, it just gives your device a longer lifetime because the heat's more pushed around faster.
Yeah. Lewis, what do you think? What'd you say? Similar thing?
It will cool down quicker.
Yeah, there's a greater
Yes,
heat
where-
dissipation, right? Heat spread out quicker, better, with more rotations per minute. Here's the problem though. Think about 1 minute of operating time, right? You operate a high-speed rotor for 1 minute. You don't, but assume you did. Operate a high-speed rotor for 1 minute. It spins 10,000 times, okay? You spin a low-speed rotor for 1 minute, it spins 3,400 times, right? Let's say they're the same bearings, the same equipment, just one time you're spinning at 10,000, the other time you're spinning at 3,400 RPM. When you spin it faster, there's more revolutions in that time, right? And your tubes have a finite lifespan. There's only a finite amount of times that thing's going to be able to spin around in its life before something goes wrong, right? So it's going to wear out the equipment quicker because in its usable time, you're making more revolutions, right? Roughly speaking, you're making 3 times more revolutions. So roughly speaking, the lifespan of a high-speed rotor is about 1/3 the lifespan of low-speed rotors. High-speed rotors are good because in angiographic medicine, angiographic radiography, you need to use small focal spots, and when you concentrate on the small focal spots, they're also making high-energy exposure. So you're making a lot of heat in a small area on the anode disc, so spinning it faster is more useful. The downside is the usable life of the equipment is going to be less. Okay. Now there are probably some smart engineers out there who have figured out how to make high-speed rotors have long lifespans by using better bearings and things like that. But again, all things being equal, high-speed rotors would have shorter lifespans than the low-speed ones. Okay. And just a reminder, the rotor rotates because of an induction motor. Here's what the stator looks like. taken off of the X-ray tube. That thing on the left of the X-ray tube is the stator. It's just a packaged coil of wires, okay? That's packaged in a really specific way, not that important, but the point is that when electricity runs through the coils of wire in that stator, it pushes it induces current in the rotor's own coils and causes the rotor to rotate. We did a whole thing about how that happens. We won't go into that. When it's all put together inside of this lead cylinder, it looks like that all packaged up. Okay, stator is in place, X-ray tube is in place, and then there's like the mounting bracketry to like hold it in position inside of here.
And the rotor only goes in one direction, right?
Yes, yeah, it's only going to spin in one direction. Doesn't matter what direction it spins, I don't think, but it's going to spin in one direction. That's the important thing. It doesn't matter what direction it spins. It does have a direction.
You're asking me.
No, I'm saying it. I'm saying it, I was asking almost like a question. I was saying it doesn't matter. It doesn't matter what direction the rotor spins in, but it only spins in one direction. Okay.
I asked the question.
Okay. Here's some important stuff. The rotor's rotation is so any moving parts of any equipment are going to be the parts that wear out. Okay. So you want to minimize the amount of parts that can wear out. So what you do is you make fancy pants ball bearings, okay, lubricated with powdered silver, okay. If they were lubricated with oil or graphite, oil and graphite would get hot enough inside of this tube that they would turn into vapor. So liquid would turn into vapor. Yes and no. They would heat up there's no air, remember, you need air for fires, oxygen for fires. So you can't catch on fire, but it can heat up so much that it can change phase, right? There's 3 phases of matter, roughly, right? Solids, liquids, gases, right? You're turning them into gases, almost into like plasmas when you're getting them that hot. By the way, there's more than 3 phases of matter. There just are. There's 3 that we talk about. But you're vaporizing the material, okay? And where does it go? It's inside of the glass tube, right? So where can that gas go?
It can go on top of to the face of the rotor.
Maybe go into the face of the rotor. Now it's taking away an area where the electrons would hit, right? So decreasing efficiency, and on the inside of the glass, right? So here's 2 problems. It's heated up. It's turned into a gas, right? But then you turn off your X-ray machine at the end of the day, and we don't have oil and graphite in our equipment. This is why. So you use it. Your oil and graphite vaporize by the end of the day. First few exposures it vaporizes. Turn the machine off at the end of the day. The machine cools down, right? Well, what happens to a gas when it cools down? Turns back into liquid, right? Or goes back in from gas to liquid to solid, right? Whatever, it changes back into its like relaxed phase at this Earth temperature. Let's say it turns back into a solid, okay? It's on the walls of the glass, and it's now dried back into a solid, okay? Or cooled down back into a solid, excuse me. Now the melting point for that vapor, which is now back into a solid on the inside of the glass, is different than the melting point for the glass, okay? So it's adhered to the glass, and it's going to expand and contract faster than the glass will, okay? You learned earlier that when part of a glass expands or contracts quicker than other parts, it tends to crack, okay? This leads to cracking. This can lead to cracking of the glass tube, okay? On top of that, oil, graphite, whatever would vaporize and get onto the inside of the glass. If it lands at the window spot, now adds extra filtration. That's more stuff for the X-ray beam to have to travel through, okay? This is not a problem because we've used fancy pants powdered silver that doesn't do that, okay? However, this is a problem. Did you guys notice the anode disc looked a little bit like used up? On top of the cracks in it, it's kind of pitted. If you felt it with your fingers, you notice that it wasn't smooth, right? All of those pits are places that used to be smooth, okay? Where did the tungsten go? It vaporized because of long use, right? Over time it vaporizes, and it vaporizes, turns into a gas, right? Cools back down, turns back into a metal again, right? But where's it going to land when it vaporizes? on the glass of the X-ray tube, on the inside of the glass, right? So we don't have to worry about this problem with oil or anything like that, because there is no oil inside of the X-ray tube. What we do have to worry about is the tungsten anode disc vaporizing. For one, it creates pits on the anode disc, changing your image properties, so the images become worse over time. But on top of that, the tungsten that was here went somewhere. Now it's on the inside of the glass of the tube. Same problems. Tubes heat up, cool down differently in different spots. They crack, ruining the vacuum of the tube. Now the tube is ruined. If that doesn't happen, it still leads to deposits of tungsten on the inside of the glass, and those deposits may end up on the window part of the glass, which again will absorb the X-ray beam. Now you don't have predictable filtration for your X-ray machine, and so it makes a number of problems that happen when there are things that go wrong inside of the tube. So engineers want to minimize the number of things that can go wrong. They can't really get rid of the tungsten. We need the tungsten, okay? But they can get rid of other things inside of here that may vaporize, like oil or graphite, that would otherwise lubricate bearings. Too hot, so we use fancy pants stuff. Okay, good, we've got that. I want to cover a couple more things, and I'm going to let you guys out of here before 1. So we're about 20 minutes to 1 right now. We'll see how much I can get to. Okay. The next thing we want is we want to learn about focal spots, okay? Let's go to here. Let's go to here, actually. Okay. So when you select a MA setting, a milliamperage setting, and you don't have to use much brain power to choose the MA setting. It's literally listed on your technique chart. Pick the body part you want to take the X-ray of. It'll tell you what it recommends for the milliamperage. Okay, you'll set that setting at some time for the exposure, and some kilovoltage setting for that body part. Okay. When you select a milliamperage, the equipment automatically chooses either the small or the large focal spot. And again, I told you, you may choose to make the adjustment on your own, but the equipment pretty well does it for you. Most X-ray techs who have been doing this for a while, if you say, hey, do this when you go out in your training, ask them, hey, are you using small or large focal spot? And they'll go, what? What do you mean? And remind them that it exists, because they remember the milliamperage settings. They want to know what the right MA is. They know the machine's going to choose the right focal spot size for us, but you may choose to do it on your own if you feel like going that extra step. The focal spot is the so there's two. Now you're about to learn, it gets a little more complicated. There are actually 2 focal spots, okay? There is the actual focal spot, that is the face of the anode that's hit by the beam of electrons, okay? So you'll notice where it has that width of the electron beam, it shows the little electrons cruising towards the anode. That width of the electron beam is set by the size of the filament that you're using, small or large filament, okay? You select one or the other. Roughly speaking, the large filament is twice as big as the small filament. So the actual focal spot created, the place on the anode disc where the X-rays are going to come from, will be larger with the large focal spot and about half that size with the small focal spot. By the way, it's about 1/4 of the size because we square it. Okay, so 1 millimeter squared versus a 1/2 millimeter squared, it's a square area. Okay, a 1/2 millimeter square, you'd need 4 of them to fit. 4 of them would fit inside of a 1 millimeter square. Okay, we're only showing you one dimension right now, right? But remember, the anode disc, looking at it from the front, is a circle. Okay, so there's 2 dimensions to the size of this focal spot. We simplify it by only showing you 1 dimension. Okay, just remember it is 2 dimensions. Anyways, the place here that's struck by the electron beam, we call that the actual focal spot. All of that. That is not a good pen. So all of that actual focal spot right there, okay? That's got a width to it. Okay, it's got a, let's say, length or height. It's also got a width this way, okay, and it's a square, okay? That's your actual focal spot. Now, so that is what you would see if you were the electrons, you're standing over here, you're looking towards the anode, that's the size of the area that you would see, what the size of the wall you're going to run into, okay? However, if you were to lay down underneath the anode and look up at it, you don't see that same size, okay? The effective focal spot, what you would see if you laid down, right? If you laid on your back with your little nose here and your eye here, and you looked up towards the focal spot, you would see a smaller area, okay? Because the focal spot, the anode's face is sitting at an angle, okay? If the anode's angle were much larger, you would see a wider area looking from down here. Okay? If the anode's face were much shallower, you would see a smaller area. Okay, so it is only the effective focal spot, not an actual thing. It's just what is apparent to you if you laid underneath the X-ray tube. Okay? However, for effective purposes, this is what the size of the focal spot is at the image receptor. Looking up from the image receptor, up from the patient, this is the actual area that the light is coming from, that the X-rays are coming from. Okay? It just appears small, but is effectively the useful focal spot size. This is a principle called the line focus principle. Let me bring up the... You know what? Do I even have it on this? No. Okay. I don't, but in a later section called Principles of Exposure, we're going to use this. We're going to talk a lot about these pictures, talk more about it, but here's something to remember. On any X-ray tube, where the angle of the anode face is less than 45 degrees, shallower than 45 degrees, typically these faces are about 17 degrees. Okay? That means the angle here from this straight line, this angle back is about a 17-degree angle, okay? Any angle less than 45 degrees, which they all are, okay, the actual focal spot will be bigger than the effective focal spot. This is something called the line focus principle. Line focus principle. It just says that for X-ray tubes, the effective focal spot, the area where you would see the X-rays coming from, if you could see it, is smaller than the actual area that they come from. Okay? The actual size is this big, where the effective size is that big, that wide. Okay? Remember, smaller is better. Small focal spot gives you a small electron beam width, giving you a small effective focal spot. A large focal spot, wider electron beam, meaning wider effective focal spot. And there is a relationship between the size of the actual focal spot and how wide it appears to us. Line focus principle says effective is always smaller than the actual. By the way, parenthetically, if this anode face were actually 40, that's not a good 45 degree. If the anode face were actually a 45 degree angle, like if that were the angle of the anode face, let's say it were, if it were 45 degrees, okay, then the actual focal spot and the effective focal spot would be the exact same size. Okay, as the angle increases, this gets closer to this size. Okay, they get closer to being a match. Okay, you want your anode face to be shallow, but not so shallow that the effective focal spot disappears. If the face of the anode were just a flat, square like that, then there would be no effective focal spot. There would just be a place where the actual electrons hit right here, and then the X-rays would scatter in all directions equally. From there, there would be no effective focal spot if there was a flat face to the anode. It has to be angled so that when the electrons hit it, the X-rays can be directed downward. Okay? Okay. It's kind of like, don't take this too far, but it's kind of like the principle of reflection with light in a mirror. Okay? If I stand at an angle to the mirror, I can see light which has reflected off of it from some angle, right? It's kind of like that. Again, don't take it too literally. Okay. Couple final notes here. all components of the X-ray tube, we said this, but let's remind, all components of the X-ray tube are encased in a vacuum. Remember, there's three things you need to make X-rays. You need a source of electrons, you need to accelerate them to some high rate of speed, and then you need to slow them down, okay? The fourth requirement, I actually almost always teach it as 4 requirements, which is what I'm doing right now. The fourth requirement is you need to do it all inside of a vacuum, because without a vacuum, you cannot let them accelerate and then hit that wall. They will all run into the little individual molecules between cathode and anode. Any molecules would get in the way, and your radiographic technique would be unreliable. You wouldn't be able to reliably set factors. Factors would change based on the density in the room, right? Air density changes with temperature and volume and a bunch of different things. So there would be way too many variables. So exactly. If you were in, Colorado taking X-rays with an unsealed X-ray tube, or down here on sea level, you're gonna have two completely different ways they're gonna interact, because there's less atmosphere up at high altitudes in the mountains, right, than there is down here at sea level. Yeah. So there would be way too many variables. Technique would become completely unreliable, and it might just not be doable to begin with. You might not even be able to create any kind of reliable X-ray beam at all, here or there. Strong Pyrex glass, forming an airtight seal, resilient to extreme heat, as well as the cooling associated with after the extreme heat. And the glass gets thin at the window. Let's finish this section by talking briefly about what happens when X-ray tubes fail, or how they can fail, okay? A couple of different things. One thing is arcing, electrical arcing. Now, where do we want the electrons to go from? We want them to go from the cathode to the anode and nowhere else, right? However, as they say here, as the X-ray tube ages, tungsten from both the filament and, remember the filament's made of tungsten too, filament and anode can vaporize and get deposited on the inside of the X-ray tube. Two bad things, I mentioned one of them earlier. One effect is increased inherent filtration. Now there's tungsten that the X-ray beam has to get through, and we know now tungsten's very dense, okay? The second problem, tungsten is electrically conductive, right? So eventually electricity from the filament can arc to the tungsten on the glass instead of going to the anode. Now you've got electricity striking metal on glass, and you're going to crack the glass. When you crack the glass, the tube loses its vacuum. Tube loses its vacuum, can't produce reliable X-rays anymore. If that glass cracks, by the way, it's not just airspace in there. There's a bath of oil around the X-ray tube, and so now oil is going to get into there. It's the whole problem. As soon as the glass cracks, you will not have a functional X-ray tube any longer. Some tubes can be made of metal envelopes. The way they work this is the metal envelope to the tube would have still a thin window, but now a metal window, okay, and the rest of the tube is made of metal. And we'll go, well, metal's electrically conductive, right? Won't it just arc to the metal? The trick is that they can, just like the focusing cup, they can run a negative current through the whole metal tube, and now the beam won't go to the metal because negative charge would repel the negatively charged electron cloud. Okay, and so it just can't arc in that case. But glass tubes, which are much more common, I've actually never even seen a metal tube. Glass tubes, they have that risk. The advantage is for the glass tubes, you don't need to run a separate circuit through the actual envelope to the tube, where a metal tube, you'd have to have an extra circuit for that. So it's just more electric components, more stuff to break. Heat damage. Excessive accumulated heat. You get warping of the ball bearings in the anode shaft. Etching or pitting on the anode surface. You guys all saw the anode surface kind of, a little bit rough, right? That's all etching, pitting on the anode surface. By the way, did you guys notice on the back of the anode, did you see the back of it, right? Look if I spin this on the back of it. It's not all flat, right? There's a bunch of these little depressions in here, okay? Do you guys know what those depressions are? Anybody worked on engines before? No? You ever balanced a crankshaft?
Yeah.
What do they do to balance crankshafts? Let me rephrase that. Have you guys ever had your car tires? Engines might be a little bit esoteric. Car tires, though, you guys all have your car tires balanced, right? When they're not balanced, what happens? Yes, but when they're not balanced, what happens?
It turns to the heavy side.
So you'll get like one heavy side of the tire and one light side of the tire, right? Your car vibrates when you drive down the road, right? You get uneven wear on your tires, right? Extra wear on the suspension when your car tires aren't balanced. So what do? As you said, they add metal weights in certain spots, right? To make the tire equally weighted all around it so that when it spins, it doesn't jiggle the suspension up and down and wear your tire out, right? Well, they can't add anything to this, right? They could actually in principle, but they won't, okay? What they can do is, in the heavy spots, they can take out material, okay? Yeah, kind of like, it's like, in engines, it's like when they need to balance the crankshaft, they will hammer out certain spots of the crankshaft, or they'll actually mill out certain spots, heavy spots in the crankshaft. In car tires, they'll just add weights to the light parts of the tire so that the whole thing is a little heavier but balanced. Okay, these holes or these depressions here are areas that they've balanced this wheel. The balancing of the wheel reduces wear on the bearings. Okay, prolonging the tube life. When the bearings go out, the tube goes out. Remember, the bearings are inside this, and this is inside of the glass tube, which is non-serviceable. So bearings go out, whole tube goes out. They don't, and they're not cheap either. We're talking car prices, buying a new car kind of prices to replace these X-ray tubes. So not cheap. You definitely want them to last, right? So we want minimal heat damage. So over time, excessive heat conducted down the anode stem to the ball bearings warps them slightly out of round, probably not even noticeable to the eye, but the equipment can notice it because it spins at high speeds. Imbalance, causing wobbling, and on top of that, right, it's not only that it makes noise and further wears the bearings out, takes extra energy, wastes energy, but on top of that, if the bearings are out of round, when this spins, it's going to shimmy slightly in all directions. The actual anode face will shimmy slightly. That shimmying is effective, is like the effect of making your focal spot bigger. So now you've got erratically changing focal spot size, lowering your image quality, destroying image sharpness. So this you could in principle pick up on an image. You could see out on an old tube that this is the case. So it's almost not even detectable, but at high speeds, at high heat, that would make a noticeable difference if your bearings got out of round. The etching, like you saw on this anode, right? Etching or cracking destroys the effective focal spot and image sharpness, so you're getting images getting worse. So heat damage to the anode, heat damage to the anode shank bearings, those are all of the major things that we consider for damaging the equipment. How do we avoid this? Well, what I'll get into next time, just no time for today, is I'll just give you the thing. We refer to which is what comes with our equipment. We refer to what are called radiographic rating charts, anode cooling charts, or tube housing cooling charts. A combination of these three types of charts to tell us how much heat we've made based on the exposures we made, and how many exposures is it safe to make before we've exceeded the capacity, and how long do we need to wait before our equipment cools down so that we can begin to use it without being in the dangerous levels again. You operate you operate your car when it's overheating, you're going to damage your car's engine, right? You operate the X-ray tube when it's overheating, you're going to damage the X-ray tube, okay? Car's engine, damage it. You might damage it so bad it needs to be replaced. Same thing is true for the X-ray machines, okay? I will not go further than that today. Next time we'll talk about heat units and then get into X-ray production after that. That'll be the first half of class next time. The second half of class will be a short review of everything we've done and prep for final, okay? You guys get out of here unless you have questions, and I will see you all next Friday.